That's good. Let's see, it's already 10 o'clock and 7 minutes. Good morning, everyone. Let's see. We could almost talk about anything of this whole semester. So I don't have the time. The SI meetings will end at the end of this week, and there's various different times, but I haven't memorized them. So you have to visit Discord and see the actual times. Over, I'm just thinking of the last 5 years, I've had 10 or 12 different SI leaders working with me, and these are these three of this semester are as good as any as I've ever seen. They're dedicated people. So I appreciate them. I didn't select them, they select me. So I appreciate them selecting this course. And I should say goodbye before the end of the week. Poe is graduating, and I think he is. I'm working on old information. I think he is. For the other two instructors, I don't know. We have to ask them. That's how I get out of saying anything. Uh, I if the other two are not graduating, I invite them back for next semester. I hope they didn't get burned out on this work. Okay. I don't have a fixed subject today, but I have a couple of documents to send you right now. I'm going to send them by chat message. Let's see how this works. Okay. Here's section 3. Right. Section 3. Section 3. Okay. Try it. Yeah, I don't have it here. Let's see. Number 1, 2, 4. Well, I sent you. No, no, yes, but use email. Okay, so I sent you class curve May 1st. Did I really send the right one? Class curve May 1st. I think I did. In the earlier class this morning, I sent them the wrong one and then it didn't match. But I think yours really is accurate. It belongs to section 3, not some other section. Okay. So I assume I sent you the scores for the last two assignments, and I can't remember. I know it's in the total. It's that midterm, let's call it the final program of about 2 weeks ago. Uh, I I don't have records here. What's that? Base. No. um, If you're missing a score in the past, pinpoint its name, like section 3, assignment 3, or whatever. Just send me that brief message, and I'll reply to it with your score number. Uh, but mostly these have been posted in Discord. If you go looking for them, you should find all of them from the past. And I sent Cole a big collection of I don't know, about 14 different sets of scores, and I'm sure he posted them. Okay. Well, last class meeting I did the, let's not do it again. It's too lengthy. I hope you kept your notes about compute the distance between two consecutive numbers, between two consecutive float numbers. Two. Okay, that's a major math problem, but unless someone has issues with it, I think my demonstration of last week was a good one. So I have an idea that we're going to experiment with. Does anybody have a question about anything in the whole semester that you'd like me to cover again for 10 minutes? Uh, Tell me in a chat message just what subject area. On Wednesday of this week, I'm going to bring the master list of all topics we've covered this semester, and we'll check them off one by one. Okay. So I'm going to remember we never did anything with it, but when you compile code, assemble an assembly function, you sometimes make, or many of you just leave it out, an extra parameter, -L, and then a file name, triangle, uh, I recommend LIS here, but you can actually put anything. So you're assembling the file triangle.asm, and this is one of the parameters of it. And I was going to spend 15, 20 minutes just looking at one of those to see what it tells us. All right. Okay, so I'm going to share a screen with you. And that's Okay, so I took Kevin's program, assignment one, to make this demonstration. In here is, no, that's not it either. Where did I put it? It's over here. Okay. You did it too. Assignment one was about the triangle and two sides and an angle between it. And so I took one of your programs, and here is the list file. So non-executing things like comments just get copied and nobody looks at them again. The declarations, global and extern, don't actually do anything at runtime, but they're important to link in missing functions, and their listing is kept there. And then when the assembler reaches segment data, it translates these sentences over here into ASCII, and that's a big wraparound line. Okay, and then ASCII gets stored here. Okay, so it takes 2 digits in hex to make an ASCII character. Now that's kind of funny. You know what 20 is? 20 is 2 times 16, 32. 32 is ASCII for blank space, but there's no blank space over here. It starts out with letter I. How totally weird. Okay, it does end with new line character and 0. So when it got translated, this, by the way, this is all continuation stuff. It continues here. And then at the end is hex 20 followed by 00. Hex 20 is a blank space. And at the end of this, it's not there either. Oh, wait a second. My bad here. That translation ended here. 0A, A is 10, and then 00 is 0. And here's the 10, 0. That was correct. And just before that was 3A. 3A would have been the ASCII value for the period at the end of the sentence. So this whole mess, I keep pointing to the wrong place. See, the hyphen mark is a continuation symbol. If there was enough space, the assembler would stretch that out across the page, hundreds of bytes across, but it can't. So it lays it out this many until it reaches there. That's the end of the first translation. The second translation starts here with there's its name, and it's please, P-L-E-A-S, and no, that is really, oh, isn't that clever? Okay, I'm looking for an ASCII uppercase letter, be around 75 or 80, and it's not there. But here is a 10, and sure enough, the programmer put a 10 there, and then it comes, please. So please would be the 50 in hex, 6C in hex, 65 in hex, until you go all the way across, and then it ends with double zeros here. And this one actually, it does end with blank space. You can see the 20 is represented by this blank space over there. So the assembler does translate all that English text to ASCII text, ASCII strings. Okay, let's go on. Here is, well, some formats are available, and it'll translate it character by character, and we see it over directly opposite in here. Each one of those translated. I was curious about how he got pi in here. Yeah. And that's, I don't know how to explain it. Pi is a pointer to a single number. But I don't know. I'll take more research than we have time. Okay. 180. Oh, no, I don't know. I don't know. Okay. Anyways, when we declare an array of 32 bytes, it gets stored like this. And I have either I don't know or I've long forgotten what is the set of question marks represent. Okay. Another feature is the counter on this side counts bytes that have passed by on the next column to it. So if we had a short string, it will add, like this one, it will add fewer bytes to this. So there's a byte counter from the start, and it plays a role eventually. Okay, so now we're inside of text, segment text, and it has to translate every one of these into a code. That has to become a code, that becomes a code. And the code is often broken up, I think we'll see that, into three components: an instruction code, and an operand code, and an operand code. A lot of these pushes have a single operand, which like this. So if the code is very small, very short, like 2 digits, it's probably something that's been as part of this language since the beginning. Later, they had to expand the opcodes to be larger number of digits. Registers R8, 9, 10, and 11 were added later, and here's the code for, what is that straight across? Push R8. I don't think you can separate those two. Look at push R9 is so right next to it. Push R10 is right after it. And in the code that gets created, the O file, it will be these numbers just lined up endlessly. 4150, 4151, 4152, 4153, 4154. It's just no spacing in between. It's just those code numbers lined up until it gets to pushing flags. Okay, that's fine. Okay, now this is generating the code for the O file, in this case, triangle.o, and some things are not yet known at the time of assembling. They are known later at time of linking. Okay. So I bet you, well, I can't prove it. I wish there was a different number than 0 here. We could see the different number. It'd be B8, and then this number would be something different. That's saying what value is to be pushed, moved into RAX. I bet B8 is move RAX. Here is 48 BF. Okay. And here's the name of a string up above, and it's going to RDI. And the reference here is it's that's a dereference of 0 from above in here. Let's see if it takes us to output info. The reference is 0, and that is output info. So in a sense, the assembler is saying that, lost my place. Okay. Put degree at 0. Okay, so we're at this line. And it's a continuation line, by the way, because that little hyphen. So there's an instruction here, and then there's something to be done, and it's dereferencing 0. But that just leads to an earlier part of this same file. It's a long message. Now, E8 always appears when there's a call printf, call fguess, call anything else. It's E8, and then there's a code number. Oh, too bad it's the 01. No, they're all going to be zeros. Even E8 here is a 0. In short, the E8 followed by a bunch of zeros says to the linker, you got to figure this out. It's not my job. So the linker's eventually going to put the starting address of printf in that slot there. E8 is the call. Okay. When there's a call, there's a whole bunch of activity takes place in memory. New activation record is created. The RBP is updated to become where RSP is. A whole bunch of stuff happens. But the linker will handle that. Okay. So pushing zeros. They're the same, all right. Oh, so I took your classmates' code and I added this part that says inserted code. What I want to do is input an integer and then show it again. Pretty simple. Input an integer, we scan F, and then we're going to output that same integer. And it's kind of interesting to know what the code is being created. What is the CPU actually going to look at? And except for filling in linker stuff, it's right here on the column, third column from the left. B8 is you can be sure that's a move, and this is all parameter. So it's a move the 0 into RAX. Let's try this one. See, this one is moving a message into RDI. Move RDI. I bet you it's this one. Okay, but what is the message? It says dereference DD01, blah, 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 blah. Okay. But we all know it's all this code is in Little Indian. So that's actually flipped over. The first thing, let's see. The last thing you would see is DD, and then before that, a 01. So in our culture, it would be 01 DD. Now but we're looking at machine culture. So let's take 01 DD and go backwards. 01 DD. And you go straight across, and it's this message called integer message, blah, 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 blah. Integer message. Zero one DD 01. It's down here. Yeah, it was integer message. So, later, the linker is going to replace this reference with the actual message itself. The ASCII text will be inserted in that place. So the instruction will read 48BF followed by all the ASCII code that is part of the message. Oh no, does that help you any? Okay, too many dereferences in here. This is backwards, of course. It references 01C4. And this is all zeros. I don't know what it references. It references names. What would all zeros be? It's not there. That is right. See, name is at address local address 000. It did fit. So, okay. Well, in forensic computing, they study this a lot. The occasion is police departments confiscate equipment from bad people, and they may not find source code there, but they'll find other code. The CIA captures enemy aircraft, and they take the electronics apart, and you have to read that stuff to see what it was doing, because there's no source files when you capture code that's running in a piece of equipment. This looks all good stuff. A lot of dereferencing. I'm not going to pursue that. Okay, so let's our intent is not to learn this, it's just to experience what some people do. So that's the list file, and it's mostly in here. This is the O file, and I should keep open. Let me see. What is it? What's something easily identifiable? Okay, let's take this one, 41415A. Where'd you go? 415. Did I say 415A? I think I did. Okay, so is this what? I'm not sure I remembered it right. Okay. Five A is right there. And so the central, the 2/3 on the left side of the screen is the code right out of the object file. And I wanted to find one within it, and it showed up here, 415A. Yeah. 415A is pop this, and directly after it should be 58. And is that, where did you go? I lost my play. Come on, guy. 58. Yeah, it's right. It's right in place. That's the code that will, I was going to say, be executed. It's the code that needs some pieces linked into it yet, but it's just consecutive instructions, no spacing, no punctuation, just consecutive instructions all the way through this. What were those two? Oh, this doesn't execute, so it doesn't do any good to updated it. Mm. I can't. Okay. So I can't do it. But if I had another, see, I could code inside of the O file. If I can't replace a two-digit code with a four-digit code because it throws off the pointers inside that file. I could replace two digits with two digits and change it within the object file. Um, I've known people who program that way. I'll tell you my personal history once. Let's go on to the next one. You're not supposed to learn to do this. You're supposed to see what the example is like. Here's the real. Did I close? This is the real executable. Open with G hex. That's called a hex edit, binary editor, by the way. And I wanted to show. Did I close the example? Let's see. Triangle. Oh, yeah. Here's where I inserted something, and there's two pops there, and that's not the good file. I should look at it in list. All right. Okay. 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 I get pop RAX. What's a different pop? 57. Mr. Okay. So if I find 58, 50, 58, and find next, I didn't change it. 50. I said one thing, did it different. Okay. 58. Find the next one. There's unfortunately there's lots of these around, and so they changed it to 57, and change this one to 57. 57. And just leave it and click save it. And close it, click exit, and save the changes. And so here it is. I modified the green one. Dot slash LEEARN dot OUP. Okay, I inserted some code that has no prompt, but it wants an integer. 34. Your last name. Trying. I don't think I don't think I damaged anything. No, okay. So there's not enough time to do it, but there's some fun exercises where you actually change the executable code using a hex editor, and it does something different. Instead of printing pi is 3.14, you'll say pi is equal to 7.995, and you can edit somebody's executable file that way. I worked at a company, an insurance company that's gone out of business, Pacific Care, for well, not a full year, 3/4 of a year. they at one point had lost their source code for their main billing program that bills uh, all the insured people pay monthly for this. And they had a billing program. And from time to time, they had to change the tax rate and change the rate of percentage withholding on people's paychecks. They did it in binary. They had no source code. Some stupid person had erased it long ago, and they kept that going as long as I worked there, and I don't know how long after. in, in total emergencies, you can do that. All right, let's leave this. Okay, how's our time look like? 20 minutes. Let's look at some instructions that kind of get overlooked. Mm, There's two kinds of shifts. One is called the logical shift, and one is the arithmetic shift. So here, for instance, shift left RAX 18. And the values in RAX will open up. This is the old one, RAX. And then the new one, after the shift left, there'll be 18 zeros over here. And some data are thrown away. That's another black. I wanted to do 18 on this side will be lost. Everybody else moves over, new zeros inserted. That's the left. Is right any different? No. Right inserts new zeros on the other side. Shift right RAX 6. Okay. We're going to get 6 zeros inserted on the from the left side. Does this preserve? Okay, before I ask that question, what it does in high speed divide by 0 or more, divide by 2 or multiply by 2. Shifting left is an action of multiply by 2. Shift right is divide by 2. By 2. Oh, the camera, why did it do that? Sorry, divide by 2. Except there's a flaw whenever it's a negative integer in here. If this is a positive integer and you shift to the left, you're multiplying by 2 for each number here. So that doesn't sound clear. Shift left RAX 7 is a multiply by 2 to the 7. Any number from 0 to 63, you can do that. It's a multiplication by 2 raised to that power. And shifting right is a division by that same power. Shift right RAX 5 is a divide by 2 to the 5. Okay. And I read, I don't really care if it's true, but they say it's faster, fewer machine cycles to do a shift than to do a full algorithm of division. Okay. But it breaks down when the number in the register is negative. Why is that? Okay. If the register is negative, there has to be a 1 here. And then there can be a, let me get a better one, various bits. 1, 0, 1, 0. That's the decimal number 10. Okay. By itself. But with a 1 over here, it's something negative. If you shift left, that's supposed to be multiplied by 2. Just one digit. The negativeness disappears, and you're suddenly looking at a positive number. 0, 0, 0, 0. 1, 0, 1, 0, and then the new guy is entered over here. Okay. This is the new guy. However, to make our lives more complex, they have introduced an arithmetic shift. That's a logical shift. That guy. Okay. So I'll show it to you briefly here. Arithmetic shift. And it looks like, why did they, shift arithmetic left, or shift arithmetic right. Now, what does it do? Okay, let's take the first one. RAX 3. Leading sign preserve. Okay. Well, this doesn't do much. I looked it up last night. It says all the bits move left. It's 3 places. The right side was filled with zeros. The leading sign bit is not preserved. Right? Filled by zeros. Sign not preserved. No. The next one's supposed to be different. Okay, I tried it. SAR BX 3. All bits move to the right. Like all bits move right by 3. And the left side is filled by the former leftmost bit. Instead of filling with zeros, that left side is filled by former leftmost bit. This one looks like the old logical shift. This one is different. And let's make it pixelated. Let's suppose I want to do it on an 8-bit register. SARAL3. Okay. AL is a small register inside of RAX. It's left, lower, A lower. Okay, so here's its picture. 1, 0. 5, 6, 7, 8. You got 8 in there. Yeah. Okay. Which one are we doing? This is shifting to the right. So you shift right one time. Let's perform a SARAL1. Okay. So everybody moves over 1, 1, 1, 0, 0. This one gets thrown out the back door. Okay. It says the former leftmost bit now fills in here. Okay. It's not a fill in by 0. Shift AL one more time. They all move over. 1, 1, 1, 1, 0, 1, 1, and the 0 is gone. The former leftmost bit gets filled in here. I think you see what's happening. Okay, so I mean, now I was doing 1 bit at a time. Let's suppose we do the whole thing at once. Here's the original. 1, 1, 1, 0, 1, 1, 0, 0. Shift AL 3 times. There's 3 blank spaces. 1, 1, 1, 0, 1. These get thrown away. Then it says the former leftmost bit, where the arrow is, fills in this whole gap. Now, what is it? It's preserving negativeness. It's a shift to the left is a division by 2, but it's preserving the sign. If the original was positive, 0, 0, 1, 0, 1, 1, 1, 3, 4, 5, 6, 7, 0. Okay. And you do it the same thing, a shift. Yes, shift to the right. AL 3 places. Okay, so 0, 0, 1, 0, 1. These get thrown away. And then again, it preserves, it's positive because the rule says it takes this former leftmost bit and replicates it as many times as necessary. Now, I don't know why they don't do this replication on where's the other one? The other shifting. Okay. SAL does not replicate the bits. Did I have one up here? We're looking at SHR, right shifting. Everything's going that way. On SHL, everything's moving left. There's no replication. The sign is just simply lost. SHL, AL. 2. There's 8 bits. 3, 4, 5, 6, 0, 1. Shifting to the left. This is in advance. It's a positive number. These two are going to be lost. And we have 1, 0, 1, 1, 0, 1. And 2 are filled in with zeros. Okay, that's a shift left. The sign is not preserved. Okay, I'm going to leave it here. Shifting right. Now on our size registers, it would be a RBX, 64 bits, VX 23, and here the sign is preserved. Okay. What else do I have? I did the divisions. Okay. Let's see. Yeah. What kind of, if it's division by, this is string, SAL. Am I using the wrong letters, class? This is, I want to show you arithmetic shifting. Oh, that is terribly embarrassing. Arithmetic shifting has to have an A in the middle of it. And arithmetic shifting, I had an A and had an A, and I think keep the A going. SAR and SAR and SSAR. Those are arithmetic shifts. The A in the middle indicates that it's a arithmetic shift. Okay. Arithmetic shifting to the left preserves the sign. Arithmetic shifting to the, say it again. Arithmetic shifting to the right preserves the sign. Arithmetic shifting to the left does not preserve the sign. This is right. Sign is preserved. Arithmetic shift to the left. Here's the left. SAL. The sign is not preserved. Well, oh, in computer science, we do a lot of multiplication and division by twos. Same way in the rest of the world, science, it's a lot of multiplication by tens and division by tens, which we call shifting the point. And it's time to end the class. There was a way it is, when it divides by 2, there's a little piece of information that goes with it. Shifting to the right. SAR divides by 2. And then my notes say that if you watch it, it will round towards zero. And yeah, SAR rounds. See, it's integer arithmetic. When you divide by 2, you're going to lose some precision, and SAR rounds toward negative infinity. Div rounds towards 0. I'm going to end with this. Let's try the one up here with SAR and see how it performs. Okay, 8-bit register. Let's take a number. We need a number to begin with. 23. 23 is 16. No eights. 1, 4, 1, 2, and 1, 1. Yeah, that's 23. So our register will be 1, 0, 1, 1, 1, 0, 0, 0. Okay. And we perform SAR on this register. First there'll be a single 1, and then I'll do it with like a 3. Single 1, it leads us to, okay, everybody slides over. 0, 0, 0, 1, 0, 1, 1. And the rules say that this former leftmost bit replicates here. Okay. What number do we have now? That's 1, 2, 4, 8. 8 and 2 is 10. It's an 11, decimal 11. So 23 divided by 2 is 11. And that's a round down. It's not 12, the answer. That was okay. Does this work when it's negative? Okay. Let's try a -5. How do you find -5 in 8 bits? I would start with +5. +5 is 1, 0, 1, 0, 5, 6, 7, 8, 3, 4, 5, 6. There's +5. To get -5, we're going to complement everything and add 1. So it becomes 0, 1, 0, 1, 1, 1, 1, 1, plus 1. Our answer is 1, 1, 1, 1, 1, 0, 1, 1, -5. Okay, let's apply SAR, AL, just stay with 1. So it's going to shift this to, everything moves right. So starting here, 1, 1, 1, 1, 1, 0, 1. This one got lost. And it says this digit replicates to fill any available space on the left. You get a 1. Okay. It's a negative number to begin with. Is it going to round down towards negative infinity, or is it going to round towards zero? That's the question. So what is this here? Okay, it's obviously negative. How can we quickly solve that? Let's flip it over to its positive value first. Okay, so all bits flip. 0, 0, 0, 0, 0, 0, 1, 0. Add 1. And that's 1, 2, 3, 4, 5, 6, 1, 1, which is 3. So what we had back here happens to be negative 3. Okay, what were we working with? We were working with negative 5 divided by 2. And we got negative 3, not negative 2. When it had a choice, the true mathematical answer is negative 2.5. Okay. In integer arithmetic, the machine has to make a choice. Is it negative 3 or negative 2? Well, the instructions say it's going to round it towards negative infinity. So it picks this one. Okay. Now, let's just use integer division. What was our starting value? Negative 5 and by 2. You put them in registers and you compute that out. This is going to give you the answer of rounding towards 0. The answer is negative 2. Okay. In this choice, negative 3 or negative 2, division chooses the answer that rounds towards 0. SAR chooses the choice that rounds towards negative infinity. By the way, when I was playing with this last night, if your number you're starting with is 37, and you shift arithmetic shift to the right by 1, what's half of that? 16, 17. It's 18. It rounds to 18. Okay. It rounds towards 0. If it were negative 37, no, I said the wrong way. I said it the wrong way. SAR rounds towards negative infinity, which is 0. But if you start with negative 37 and you shift it by SAR, it doesn't round close to 0. It rounds to negative infinity. So this would be, answer is negative 19. It has to choose between, mathematically, it has to choose a number on one side of 18.5 negative. It chooses the one that's further away towards negative infinity, and that's why you get this answer. If it's this one, you get this answer. With SAR, with division, you get the answer that's closest to 0, no matter if it's positive or negative. You're probably tired of that. I'm going to leave it there. Wednesday, I'm going to run through, we just got to name them and discuss it for 1 minute on each topic. We're going to run through every topic of this whole semester. And it should ring a bell in your mind. And you'll say to yourself, yeah, I saw that before. I saw that before. Okay. And the clock is past 11. Have a good day, everyone. We'll resume this, the last meeting of this semester. You can go under the camera, right? There. For those who are recording this, I didn't line this up well. The story started there. And the next slide was SAR and SAL. But there are some examples worked down. But arithmetic shift, SAR is a preserved one. That's the interesting one. SAL is not interesting.